thank you again all for coming. Adrian, I welcome you to the stage. Thank you for helping us.
Okay. So it's Community Day. Thank you, everyone, for coming. I'm wearing actually a community shirt that I got in Australia. They have a Cloud Warriors is the community program they have there, so I thought I'd wear that. Today, actually, I have to go away, whatever this thing is. All right. There we go. All right. So I was asked to do this talk because I don't really have a talk anymore because I retired. And then I thought, why don't I just do the old talks that I gave over the years? Like a classic rock band on the annual We're Not Dead Yet tour, right? And I'm sure some of you have been to the Mountain Winery, like Chicago were there recently. Like, are they still alive? You know. So you go to the Mountain Winery and you find out that these bands are still touring. So I figured you just want to hear the hits, so I sort of assembled some stuff that I thought was interesting going back a little while. Headbanging is optional. That is actually a picture of me in 1982, and we have a set list. So we're going to open with a Black Tiger playing Don't Look Back, which is, you know, what I was thinking when I was 21 or 22, but now I'm 62. So 40 years later, I'm going to look back, right? So we'll start with that. Then I've got a talk. The first talk I ever gave about cloud was at the Computer Measurement Group in 2009. So I've just got a few bits of that. And then a couple of the Netflix talks from QCon San Francisco, and then a Cassandra Summit. And then I'll move forwards a bit to, as cloud was starting to pick up, some of the cloud trends I talked about in 2016. And then I did a whole bunch of, and when I joined AWS, I got a budget to like, my graphics art skills are really woefully inadequate, but I got a budget and a company, and I sent them money, and really cool decks came back, so my favorite decks from that era. And then if there's time, I have an encore. We'll talk about bottleneck analysis, just because I think it's cool and geeky, but whatever. All right, so we're going to go for Netflix, but first of all, I'm actually going to switch here to, where's this thing coming? All right, let's get back to this. This is an old laptop. I had to give back my nice work laptop when I left, unfortunately. But I think this will actually play, so let's see. And I'm going to do a little bit now. All right, there we go. We're now Netflix. It's a good bit. It's the headbanging optional. Right, okay, that's enough headbanging. That was a cassette tape of the mixing desk back in the day. It's all right. No, that was all I wanted.
Oh, okay. You want to play it again?
No.
No.
Do you want to play it? Do you want to hear it again?
Yeah, I didn't hear it. That's fine.
Yeah? No? All right. Okay, let's go back and have a bit of headbanging. I'm playing bass, not lead guitar, just to make it clear. Okay, that was all I wanted to do there. Thank you. I'm just going to have fun with this, right? So that's the general idea. Okay, so I now have on one of my Netflix T-shirts, and it says, "Now with more Emmy." And you might not realize Netflix has won lots of Emmys, right? The very first Emmy Netflix won was for technology. And I think Netflix has two sites at the time. There was Los Gatos, and there was Beverly Hills. And I think the Beverly Hills team were pretty pissed off that the Los Gatos team got the first Emmy for technology. So Netflix's first Emmy was a technology Emmy. It wasn't for any content they'd done. It was not House of Cards. This was before House of Cards and stuff. So we got this, and we sent our chief product technical guy off at Neil Hunt went down and received it, and they brought it back to Los Gatos, and we all got pictures taken with it and stroked it, and it was all very cool. So we had this T-shirt made because we had an Emmy, and then the LA team went, we need to make content so we can earn Emmys as well. Anyway, so I'm going to wear this while I do the Netflix talks. So 2009, I'd been in the computer measurement group for a long time. It's a bunch of mainframe capacity planning people that were sort of dealing with some of the Unix machines and whatever. And so I was trying to explain cloud computing to them. So this is cloud computing, right? Small cloud plus small cloud equals bigger cloud, right? That's computing. Small cloud minus cloud is sunshine, and sunshine plus rain is rainbow, okay? That's cloud computing. These are the basic elements. So it seemed like that was hopefully going to get them going. But really, this was a capacity planning conference. So, well, what is capacity planning? It's about all the different resources, how well your application's behaving, how much resources you're using, how much headroom you've got, how that's varying. So it's about the behavior of systems, and it's something that I've been working on for a very long time. As was mentioned, I wrote a book on Solaris going back in the 1990s. So this has been like for over most of my career, I've been worrying about capacity planning and performance and headroom. And these are the norms of capacity planning. This was what all of the people at this conference were struggling with every day. But when you get to clouds, capacity isn't expensive anymore, and it doesn't take any time to buy and provision, and you can shrink it. And it doesn't come in big chunks, and you pay for it after you've used it instead of before you've used it. And you don't have planning errors. You can just change, right? Everything is much more fungible. And particularly at the time, systems were definitely not clearly defined assets. There's a machine out there somewhere, you're not quite sure what kind of machine it is. And it's getting better now, but certainly in 2009, it was very hard to get instrumentation on those. We've moved on a bit, but we've also gone back, because now, has anyone here got an AWS Outpost? Right? Okay, so now there's a rack of hardware where it's expensive. It takes time to arrive. If you buy it, you're stuck with it for 3 years if you buy it. You have to pay up, basically you have to commit to it to get it. So we're back. So we have to go and learn capacity planning again, because now the cloud has been distributed to the point where we're delivering it all the way to the edge in chunks where it's not as fungible as if you have that central pool. So anyway, this talk I was trying to explain cloud to a bunch of mainframe people, and it was, I think, baffled incomprehension was probably the basic response to it. There were 1 or 2 people says that looks like it might be interesting in a few years, and that was about as far as we got with that talk. But there was one more slide, because what I was telling people was there's this thing called Hadoop, and actually, I'm going to tell a little Hadoop story. So 2008, there was a Hadoop summit that I went to. Some friends of mine that I knew were there. Actually, the product manager for Hadoop at the time was another ex-Sun person I knew. So I got into the Hadoop summit, and most people had not heard of Hadoop. And then I hired somebody, it's Shashi Madappa, who's still around the Bay Area somewhere. So Shashi was joining my team, and he said, well, I joined in 2 weeks. What shall I do in the meantime? So why don't you learn this Hadoop thing I've just heard of? So he turned up on day 1 and in the office, having spent 2 weeks just deep diving on Hadoop. And we found 4 ancient PCs. And we stuck them in a cube. And we networked them together. And we got Hadoop running on it. And then we ran out of disk space. So we went down to Fry's and bought 4 1 terabyte USB backup disks and hung those off the 4 things. So we had a 4 terabyte Hadoop cluster. And then we started just messing with it. And then another team sort of found we were playing with it and started messing with it. And a bit later on, they say, yeah, can we have some more capacity on that cluster? And we walked them to the cube and said, this is your cluster. It had a sticker on it saying, do not touch any of this stuff. They went, we're running on that? Okay, let's go and get a real cluster. And then we hired somebody who really knew about Hadoop, Eva C, and Eva took over Hadoop, and my team started running it. But I was kind of proud to be like the first people to run Hadoop at Netflix back in 2008, 2009. And then AWS came out with EMR, and it went, okay, we never need to provision a cluster again. You just make an API call, and a Hadoop cluster appears. So this talk basically was trying to explain that to a bunch of mainframe people. But this is talking about security things here. So if you're putting your data in the cloud, what are you doing? People were worried about it. So the security was good. This is my kind of position, and I think this still holds. You're a few clicks away from making your data public, so you need to think about that. We still keep seeing S3 buckets that are public. Get permission, scrub data to remove sensitive information. But system performance monitoring logs don't really have sensitive information in them, so they were a fairly easy thing to get permission to move to the cloud to analyze. That was my pitch to them. Anyway, like I said, I think that still holds. So that was 2009. So then, towards the end of 2010, I did a talk at QCon San Francisco, and there's a guy called Randy Shoup, who for many years has been doing a thread called Architectures You Always Wanted to Know About. And I used to work with him at eBay. I think he's currently the chief architect at eBay. And he said, why don't you come and talk about Netflix? So I got permission to talk about Netflix and wrote this deck. And then we did all pre-run at some kind of cloud dojo thing. Actually, Dave Nielsen, were you there at that one? Do you remember that talk? Anyway, Dave, we used to go to these cloud camps that Dave organized back in 2009. We were all figuring it out. So if you want to know the history of cloud, it was at the Cloud Dojo. Do you remember that place? It was some kind of weird building in Sunnyvale. Yeah. No, I think it was before that. Anyway, whatever. So I did a pre-talk where a bunch of people came, and that was interesting. And then I did it at San Francisco. And so I want to run through some of this talk to see what we can learn from it. So the first thing I want to explain was why was I even giving this talk? And it was because we were pathfinding. We wanted to share with and learn from the cloud community. So we're still doing that kind of thing. The other thing was there was a lot of activity then to build clouds. The vendors wanted to sell you clouds for your data, to build a cloud in your data center. But I wanted to talk about how to use clouds to build applications. So that was the level I was at. I don't really care about what it takes to build a cloud. I've always been above the API trying to make it do something. And I thought it should be open source. So the other thing that Netflix had was all the technology we were using was open source technology running on the cloud. The other thing was, hey, we were looking for talent. We built a technology brand as part of this, doing these talks. We were deliberately building a technology brand for Netflix so that we could hire better engineers. And that worked out pretty well as well. And we'd also stopped building our own data centers. We were running out of capacity. We saw data centers as a large inflexible commitment. You have to plan too far in advance. We actually don't know how much data center capacity we're going to need in a year, except that we know if we try to build one, it will be wrong. All right. And streaming was growing at 145% at that point in time. So we thought we'll leverage AWS. It was the biggest cloud at the time. It still is. All the investment zones, we were finding AWS skills and resumes. And at the time, we thought that AWS was 2 years ahead of the other clouds. And I know you could argue, depending on what you're looking at, whether AWS is still ahead in some areas and others it's more even. But this was the set of services that we had in 2009, 2010 to use. And of course, Werner Vogel's quote, undifferentiated heavy lifting, that's the original quote. We just kept repeating that. We don't want to do undifferentiated heavy lifting. And I took the axes off this. I think the peak of the red line here is somewhere like 5,000 to 10,000 instances, something like that. So this was, the red line is encoding, because a bunch of movies get delivered to Netflix, you need to encode them for delivery. So we'd spin up a huge cluster to process them. At this time, all of these clusters, the encoding software actually ran Windows. So Netflix was the biggest user of Windows on AWS, and we were using this encoding engines running the Windows software to encode to the Microsoft streaming formats. So, AWS we have Microsoft Windows, and what are you actually using it for? Encoding videos. Anyway. And you can see a gradual increase in test and production, and then a log analysis. And this is actually the account structure that we used. We had an account for prod, account for test, account for encoding, an account for the data science team. And that was how we broke it down and moved forward. So then, let's look a bit about what we did. So these are some of the goals we had for moving to the cloud from the data center. We wanted to be faster, scalable, available, productive. We wanted to change some things that we were doing in the data center for the cloud. And we wanted to, there's a whole bunch of talk about developer bring up, how we did that, and then some roadmap. So detailed goals. We wanted better latency than we had in the data center. I mean, some of that comes from coding, some comes from just where we had better bandwidth into AWS than we had in our data center, because a single data center just has whatever you've provisioned. We wanted to avoid needing any more data center capacity, wanted better robustness and scalability, and we wanted no scheduled downtime. There was a time, if you remember Netflix on DVD, where if you tried to visit Netflix on a Thursday morning at about 1 a.m., the site would be down for maintenance, because we had to change the Oracle schema and bounce Oracle. And a team would stay up until 1 a.m. on a Thursday morning. No, it's Thursday morning, right, Wednesday night, Thursday. They'd stay up late on a Wednesday night into Thursday morning, and supposedly it would take about half an hour, but every now and again we'd come to work and they'd still be trying to get the damn thing back up and rolling stuff back, and 6, 7 hours later they're still trying to get the update to happen. So we wanted to stop doing that, partly because it was annoying to have people that had to every couple of weeks stay up late. Partly we just wanted it to be on all the time, because streaming, people that want to watch TV at 1 a.m. is a core demographic for Netflix, right? It's amazing that you get sort of security people with games consoles watching Netflix on them at 3 a.m. It's like the proportion of people watching on Nintendo DSs at 3 a.m. is actually surprisingly high. So then we went to, these were the things we wanted to stop doing. We wanted to move from a central SQL database, we had this big Oracle system, to distributed key value. We had sticky in-memory sessions, wanted to get away from that, to using memcached to hold the session data. We wanted to go to latency-tolerant protocols, untangle all our code, instrument the code so that you just got it by default. All your instrumentation and monitoring and observability was baked into the patterns we were using. Lightweight serializable objects, and the developers up to that point, their output was a jar file. The developer would work away and they'd build a jar file and deliver it to the build tools, who would smash together all the jar files, try and make it work, and that would be the monolith that we deliver. And so, no, you're going to take that jar file, you're going to put an API in front of it and run that as a service. And that was sort of the transition for the developers. So then they had to learn how to run what they'd written. Architecture looked a bit like this. At ELB, we had our own API proxy. That redirected some traffic to the data center and back. These slides are all up on SlideShare, so, whatever. They're all old decks. memcached, and we had SimpleDB. Remember SimpleDB? It was sort of a weird layer over the top. Underneath SimpleDB was actually a little MySQL instance, and we overdrove it sort of about 100 times beyond its advertised limit for what you were supposed to do in it. So one of the problems we ran into at this time was we were killing part of AWS by overdriving it more than we should. So then what we were trying to do, so we're going to move systems of record. So at that point, in 2010, we had the front end of Netflix in the cloud, but we didn't have the databases. The systems of record were still in the data center. So what we wanted to do next was move the data to the cloud, cut that replication link. We were thinking about global expansion. We wanted to optimize for video encoding, and we thought that cloud standardization would come along. But we'd also want to be an insignificant customer in a giant cloud. So one of the reasons why we started talking about this was to get more customers on AWS so that we'd be a smaller proportion of AWS, right? And one of the analogies I like to use is you want to be a small fish in a big pond, right? That's the way it works best because all the fish swimming around don't really care how big the ocean is, right, or the pond is. If you're a shark in a paddling pool, like every time you twitch, something bad happens. Right, and at times Netflix was a shark in a paddling pool for some services in the early days, and we were just had to be really careful what we did. And every now and again, we'd get a call from AWS saying, "Could you stop doing whatever you're doing? You're breaking something." And vice versa, we'd call them and say, "We're about to do something that might be big. Can you let us know?" Whatever. So we got good at that. Response to this. QCon San Francisco is a pretty progressive conference, but I think it was basically incomprehension and confusion was the basic response. It certainly wasn't, oh yes, we're all going to go off and do this. So nowadays this maybe is hard to understand that it was really a very radically strange thing to be proposing, and we actually had people saying, you guys are crazy, you will be back in your data centers pretty soon because this isn't going to work. Right? That was generally I was talking a lot on Twitter, I was getting that a lot. Okay. So then, July the following year, we'd moved Oracle to Cassandra, over about the 6-month period. And this is one of my favorite slides. I was saying, these are the things we don't do. We don't wait. We don't get stuck with the wrong config. We don't ask permission. We don't run out of space and power. I don't plan in advance. We don't have meetings with IT. The developers are writing code that provisioned systems directly. We didn't have storage admins. We didn't have data. Well, our database admins became Cassandra admins, but they just were developing code to deploy Cassandra. And then I updated this slide a bit more. Yeah, we couldn't build data centers fast enough, so running away from an exploding data center was kind of where we were at, really. We were launching on iPhone. So we had a customer base of about 10 million or more customers at this point, and every time we turned on a new platform, we found, well, about a couple of million of them had Xboxes or something like that. So when we turned on Xbox, there's a huge, like, immediate, day one, 1 million people used Netflix on Xbox. Like, all the APIs had to work. And we did the iPhone was probably the biggest launch because we had millions of people visit almost on day one. You didn't have to go home and get your Xbox out. You could just like, hey, I can do Netflix on my iPhone now, right? So this is the capacity, the growth and the capacity. So our data center capacity is the red line, and we've basically blown right by it. We no longer could move back to the data center. So the early transitions, we could go back and forth. So then we transitioned Oracle to Cassandra, SimpleDB and Memcached, we put that in Cassandra. And then we had to do backup, restore, think about business intelligence. So the architecture looks a bit more like this now, gradually getting off of SimpleDB. We had high availability by putting copies in 3 regions. And this is actually, I went to Google Maps and went to Ashburn, and I think these are actually Amazon buildings that I found on Google Maps. And I was sort of partly guessing and partly Googling addresses and things. So I basically decided these were the 3 zones we were using, just like a picture. AWS won't let me do slides like this now, but anyway. I have no idea at the time. So the idea was that when you wrote to Cassandra, it would store the data in 3 different buildings, and that would take a millisecond or a few milliseconds. And that was our sort of basis. And then if we wanted more copies, we could scatter them around the world. And this is the Australian map of the world, so you can see. Any Australians in the audience? It's the right way up. And the nice thing is it's got Hawaii's in the middle, and I think Hawaii should pretty much be in the center of the map, because wherever you are in the world, you need to know how to get to Hawaii for a vacation. So we were doing all these things. We never actually did deploy everywhere, but the plan was to deploy sort of 3 zones in different regions around the world, and it ended up being East and West US and Europe, but that was where it was. So then the question was, how do you do backups in the cloud? And one of the nice things about Cassandra is it writes an immutable file to disk, and every now and again it compresses and combines these files and then deletes the original ones, right? So it's basically a continuous sequential write is what you see at the disk, and then it closes the file, and then it starts writing another file. And this is beautiful. So what we had to do was copy these files to S3 and back them up. So how paranoid was I going to be? Well, the local file on the disk, you could use that as a backup, but if you had to restart Cassandra or you lost something. So I said, okay, we'll copy that to S3, and we'll base restores off of just copying the files back from S3 to Cassandra and restarting Cassandra. So that made sense. But then archives could be stolen, so let's encrypt the archives as we copy them to S3, so that made sense. Well, the region could have a problem. So let's copy them to another region to do that sort of every other day. And the production account had have an issue. So let's create an archive account that has its own, that just does nothing but store backups. This is just such a simple platform. I don't know why anyone doesn't do it this way. Put a no delete S3 ACL when you have the overwrite, the versioning flag turned on. So if you write the same file twice, you just see both versions. You can't delete files. All you can do is copy them there, right? And then basically everything we had that wanted to save stuff just copied data to this account, which was homed in a different region. And then because at the time, this is 2010, 2011, we thought AWS S3 might have a global problem one day, we actually made another copy in another cloud vendor. And for a long, long time, Google would say, hey, we're Netflix, we have Netflix cloud stuff too. All they had was the S3 backup copy. I think there's a bit, they maybe do a bit of machine learning now, but for years and years, they would get all like excited because they were Netflix. Yeah, all they had was like the second backup copy in case S3 ever died globally. And then this is, I think, one of the first times I ever talked about Chaos Monkey. We wanted to make sure any instance to fail without customer impact. And if you think about an autoscaler scaling up, you're just adding instances. That's fine. Scaling down, you have to remove instances. So do you want to have to kind of drain the instance carefully before you... No, you don't want to do that. You want to basically just turn instances off and have the autoscaler shrink down. So that means it must be OK for an instance to go away at any time. And the Chaos Monkey would just take an autoscale group and just kill a machine. And the autoscaler would go, oh, I'm missing a machine. I'd put it back. And that was all it was doing. It was just making sure you could scale down and that there was no stored state on anything that couldn't be retried. So it was like a design constraint that we had stateless services. That's really all that Chaos Monkey was trying to do. And it ran Monday to Thursday, 9 till 3, and every now and again at 9 o'clock something would break and we'd figure out what had gone wrong. We had a no-ops organization. I was eventually asked to stop using the word no-ops because it was pissing off the ops people, but we didn't have an ops team, and all of our stuff was provisioned directly in code instead of using, somebody said we were doing it wrong because we weren't using Chef and Puppet. It was like, we have developers, they don't want to use Chef and Puppet, that's ops tools, right? We have dev tools, and the developers wrote code that made machines happen. It seemed like that was easy. Anyway, by this time, people had agreed that this did seem to work. But it only applied to, we were a unicorn. Like, no one else in the world is ever going to want to run like Netflix. It's completely, you guys are weird. You're some weird unicorn. I switched my, my Twitter icon to a little picture of a unicorn on a cloud. And it wasn't relevant to anyone else. But it was interesting. And it seemed to work, but no one, and there were a few people doing this, but like the people at the big banks and whatever were going, no one's ever going to do this. All right, so it's time to do another switch here. I did tuck in the bottom layer so that you don't. All right. And this is, it's the 20 years of open source team. So anyway, it's actually a bit later, but I don't know what, I can wear too many layers for this thing, it'll get too hot. All right. So in 2014, GigaOM and GigaOM no longer exists, but it did a conference called Structure. And I did a talk there called Cloud Trends. I wanted to just do a talk about because I was an independent at this point. I was working for Battery Ventures, and I could talk about whatever I wanted. So I basically went on and was talking about, this is what I think is happening in cloud, this is what I think is going to happen next. And I didn't have any NDAs with AWS, so I could just guess what might happen. And I gave it a few times. So this is a nice graphic from Simon Wardley. This was what was happening at enterprise. The enterprises were they were going to ignore cloud. Netflix was doing it. Then the rest of the world started copying it. They were still ignoring it. And then eventually they'd go, I said no, damn it. And then, oh no, and then, oh shit. I'm sorry. All right. No crap, whatever. And then they'd start adopting it. So in around about 2014, enterprise IT really started adopting cloud because they were getting overrun by cloud from all directions and they couldn't hold it back anymore. And then this is in 2015. Lydia Leong, who's a Gartner analyst, follow her, she's awesome. She said in 2014, what a difference a year makes. In this year, everyone's comfortably using infrastructure, AWS, a bit of Azure. So that was interesting. And a year after that, I posted this tweet, which was a comment from the stage at reInvent. We can operate more securely on AWS than we can on our own data centers. Rob Alexander, CIO of Capital One. All right, and I'd been advising Capital One around that time as well, working with them a bit. We're really seeing serious movement of banks to the cloud in 2015, right? So you just all up, this unicorn thing, we sort of moved on at this point, right? So then we get to the enterprise vendors because they see cloud moving along. So what was the response of the big enterprise vendors at the time? Do you remember this? So Dell basically took itself private around this time. So this was my Dell going private thing. Yeah, the ship's sinking. Let's rebrand as a submarine. Sorry for anybody from Dell in the room. EMC decided to merge with them. That looks like a great idea. We're thinking too. Let's go merge with you. So Dell EMC became this private company, right? And then HP was like dividing itself in two at the time. So like all they could talk about was how they were managing to split their company in two really quickly. It was technically a hard thing to do, but anyway, one of the GigaOM journalist said she was just laughing hysterically in the front row when I was giving these slides, so that was cool. Anyway, so I signed to a new label, much, much better pay rate at AWS. They somehow took me on as a VP. And had a much bigger production budget, because as you can tell, my graphics art skills are really not that great. But I found somebody who was a fantastically good graphic artist, and I paid them money, and I sent them these really scruffy-looking sketches, and they came back with lovely animations. So now I'm going to run through a few of those. And this is one of the early ones we did. So I want to talk about denormalizing databases, right? And at Netflix, we used to talk about this, and we used to say, you know, that Oracle database schema is like a kitchen sink of garbage. It's just got stuff thrown into it, and it's got so complicated you can't change it without breaking it. And that was kind of where we got to. After 8 years of continuously updating our Oracle database schema every 2 weeks, it got so many changes, it became too fragile. And that was one reason we ran away from it. So we have a kitchen sink, and we're going to denormalize the kitchen sink. So the problem with monoliths is they're hard to create and run, and so monolithic databases have the same thing. They're just hard because there's too much stuff tangled together in them. And your schema looks like that, and then you keep adding stuff to it. And when you go to say, I need to add a new thing, and you go to your DBA team, and they've got a big Oracle database, and they say, oh, we'll just add another table, right? And that's the way they think. They don't think I can start, because it's hard to start a new database. So it just gets to be a big mess. So the kitchen sink analogy, and this was the fantastic graphic arts here. So you think of a student accommodation kitchen sink, right? Shared house, that kitchen sink, right? It's full of broken glass and dirty water and stuff. We want to clean it up. So what we're going to do is we're going to pull everything out into its own little thing. So we've got a place for spoons. We're going to go to a place for knives. We're going to pull out the glasses. We're going to pull out the plates. But then actually it turns out we've got a consistency problem because we're short of a spoon. So one of the things you have when you have one central database is you can enforce consistency rules on it to make sure everything's consistent. And when you denormalize, you have to figure out an external way of maintaining consistency. So it turns out it's an easier problem to solve for consistency across databases than it is to scale and maintain a monolithic database. That's my kind of argument, effectively. So, all right, so we figured that out. And then we go, okay, we're going to add a new use case. We're going to have some Japanese food, so I want some sake and some bowls. And I'm going to do it by, instead of throwing everything in the sink, I'm going to add a separate place to do it. So, right, so going to look at cloud, it turns out you make an API call and a database appears. But you don't have to go and talk to your DBA team and beg with them to add a table to Oracle. You just API call, another MySQL, Postgres, whatever. Databases just appear on demand. So you stop adding new things to the central database. You start surrounding it by add-on databases. And then you start untangling things and pulling them out until what you've got is a bunch of very simple, just a table with an index, or maybe a couple of tables with an index, and it's a single-purpose back-end for the front-end. So if you might have heard this microservices pattern of back-end for front-end, you've got a front-end microservice. It has a data store behind it, and no one else talks to that data store, and it just has the stuff that thing needs. And if you want that data, you talk to the service, and the service will give you the data. You don't ever talk directly to the data store. So that's kind of the model. Anyway, so I had fun with that. And then I was going around at conferences doing talks, and I was running into serverless and started seeing some really fast delivery. And I started talking to audiences saying, I'm seeing ridiculously quick builds, people building stuff serverless, like super fast. And people started telling me stories. And I went, oh, that's a cool story. I'll start retelling the story. And then I tried writing it down. So these are 2 stories that I got. And I have an iPad and an Apple Pencil, and I just scribble something on my pencil, and I sent it to this graphic artist, and they came back with these lovely slide decks. So here's the first one. Someone said, well, we had about 20 people. We were going to work for 9 months to build something. We were 7 months in, and we were nowhere near finished. We'd done, like 30% through. And the guy said, me and my buddy were sitting there on Friday lunchtime, complaining about this and saying, damn it, if we could build this serverless, I think we could build it pretty much everything in a few days. And they said, well, I'm not doing much this weekend. Partner's out of town. I was just going to goof around anyway. Why don't we just go do it? So that basically they went, all right, let's just see how much we can build by just going away. We know what we're building because the spec was done. So they just went and just worked through the weekend. And they just coded away. And the functionality kept coming. And they were making good progress. And by sometime on Monday, the entire functionality of the whole project had been written by 2 people working through a weekend. This is a story I'm getting. Anyway, so then they went to work, and then they spent the next month convincing everyone else at the company, one, they had finished the project and it did work, and it was safe and they could deploy it. So like everyone eventually went, okay, I guess let's deploy this thing, because you're done, right? So they ended up shipping the entire application a month early. And pretty much just the code that they built that weekend. So I start telling that story, and then somebody tells me of another story. So let's go look at this. This is a sizing discussion. There was some ancient mainframe app from 20 years ago that was running. It was critical. It wasn't particularly big, but it was like sitting there running. And we'd really like to get rid of it off this mainframe. And some solution architects talking to the customer. I was talking to the solution architect. They relayed this story to me and said, okay, well, it's like a couple of weeks in serverless we could build that thing. Oh, wow, that's fast. But how much is that going to cost to run? We're paying IBM $1 million a year to maintain everything around this, not just the hardware, but the management and the updates and the support and all that. It's $1 million contract. So, well, how often does everything happen? What's going on here? And they kind of give some data, do a bit of analysis. Well, that's less than 1 million functions a month, so you get that for free. You replace a mainframe with Lambda within the free tier was basically what was going on. Well, that's ridiculous. Well, obviously, it's got storage. And so, okay, how much storage? Well, 15 gigabytes was a lot 20 years ago when mainframe. It's a lot of mainframe storage. But, well, you get the first 25 gig of DynamoDB for free, but we'll charge you $6 a month to get point-in-time continuous backup. And they said, okay, can make this look like it costs more? I think in the end, they did like a $100,000 professional services contract to do this and anything else they wanted to do, to just make it look like something they could go to management with that wouldn't look stupid. All right. So anyway. And this is a kind of, it's a story I heard, but this was sort of resonating, and then there are actually links here. There were a couple of mainframe migration to Lambda stories that I ran into. Not exactly the same story, but similar. But anyway. So it really just turns out, though, a lot of corporate IT apps are pretty low utilization. You can replace them with a Lambda function if you work at it for a few days, right? That's sort of the state of the art, really. But they're complex workflow, so step functions is pretty good. So rewrite these things as serverless. So then I started thinking, what is different about serverless? And this was actually the first deck that I got this graphic artist to do. I said, I want to have a monolith, and I want to show this big monolith, and I want to show the monolith breaking into microservices. And it's like, and they did this, and I don't know how you do that in PowerPoint, but they did that, all right? So I paid somebody else to do that. The slides, the code for this is on GitHub if you want to go stare at PowerPoint and try and figure out how they did it. So then the point is that you've got microservices, but inside that monolith was an object store, and there was a queuing system, and there was some event management, and there was an API front end, and these were all part of that monolith. But when you break it into microservices, you break those out, and you don't build microservices to do those. You just get those off the shelf. So you use the AWS services to replace. About half the code in your monolith disappears because it's just off-the-shelf stuff that the platform does for you anyway. And then the bits in between are your business logic. All right? The bits you still have to write. But you can break those up, and you can connect them, and you can turn those, and you can break up those microservices into Lambda functions. And then I sort of grayed out the whole thing because it's not running. And this is the point, is it's not running until something happens. And then I have this. And I know that this isn't actually how Lambda functions work, but it looked cool. Right, you never really daisy chain through a bunch of functions to get something done. But it's sort of, the idea being, I was trying to get people to understand that stuff is only there when you invoke it in this sort of event-driven model. So anyway, so that was like the first little one of these slide decks I did. And then, so why is it so fast to write these apps? So now I have an analogy. The user need is a suspiciously familiar-looking spaceship, usually available as a Lego model from one of the vendors in the expo, pretty much anywhere you go. So the problem we're trying to solve is to build this model. And the way you do it traditionally is you do a prototype, you carve it, you make molds, you produce some parts, you assemble them, you discover it doesn't work properly, you go back and make some new molds, you go back and forth a few times, and eventually you have a finished toy. And some of you as kids, or you've had kids, you've got this toy. And about 6 months later, all the loose bits have broken off and it's sitting in a box somewhere and you're not playing with it anymore, right? It's got a kind of a life, they wear out, right? But that's kind of, you buy it for Christmas and it's this big shiny toy. So that's the traditional approach. And the rapid approach is you get a big bag of Lego bricks, you get the instructions, you just spend a few hours, and then you get the best PowerPoint animation in the history of PowerPoint animations, because I don't know how you do that. I'm just going to do it a few times. All I said was Lego spaceship. I sent those 2 words to somebody, and they made this. And yeah, I don't know. I just love that. I'm going to play that over and over again in a loop. Anyway, now, it's got sharp corners on it, right? It is not exactly the same as the fully, it doesn't look the same as the one in the movie. It's recognizable. You can modify it and extend it. You can add bits to it pretty easily. So that's actually, was the plastic toy version you can't really extend. And then what you can do is say, well, what Lego does is they take things like nose cones or whatever, and they say, that bit's too clunky. I'm going to develop a new Lego part that makes this part look better. So Lego now, I mean, when I was a kid, Lego was just bricks and windows, and you can make houses out of it, and that was it. And you could sort of, maybe you had wheels. And now you've got little people and nose cones and all kinds of weird shapes. So the number of distinct Lego bricks has become enormous, right? But what they're doing is they have the standard ones and then a few custom ones. So what you're doing is, as a post-optimization, building this custom component. All right. So the idea here is that rapid development, you're just using building blocks. It's hours of work instead of months of work. This is why serverless is so fast, right? It's standard, reliable components that are scale, well understood, you know how to plug them together. But you have to adjust your requirements to fit the patterns available. Like, you can only build this model at certain scales out of Lego. It doesn't work. You can't do the half size. Whereas at full custom, you can make it any scale. So you have to add constraints to what you're trying to do it. But the constraints reduce debate. There's only one way to do this, so we do it that way. We don't have to have an argument about it. And there was something I said once was, if you have 2 teams that are having a race, you've got a Kubernetes team and a serverless team, the serverless team will have finished building the application before the Kubernetes team have decided which version of Kubernetes they're going to be using and how they're going to deploy the thing and all this stuff, right? You can spend longer arguing about your technology stack than it takes to build the actual thing. But it's not that you don't need containers and Kubernetes and things like that, because these custom parts, so you post-optimize. So the idea here was the first thing you should do is build a serverless version of whatever you're trying to build, because it will only take you a few days, you'll learn something, and it may be all you need. But there'll probably be a few bits that don't work quite well enough, and then you just find those bits, and then you build those as containers, or you do something more custom for them, right? So the idea being that you should always do serverless first, but it's not serverless only. It's like Kubernetes is an optimization that you use for the things you can't do on serverless, like you might need GPUs or something like that. Okay. And then there's a whole serverless first talk I gave once, but I'll just use one slide from that. These are all the excuses why people say they won't use serverless, patterns, portability, languages. It supports all the languages now. It's scalable, resilient. The latency keeps going down. There's interfaces to databases built in now. There's lots of examples how to get started. Security, all these things, state handling, event processing, there's lots of things here. Anyway, it's all complicated, right? So that's how much more time have I got, by the way? You got time for an encore? Or a few more bits and some drinks? All right, so that's also me on stage with Black Tiger. Anyway, new wave of British heavy metal, there you go. So I'm going to talk about bottleneck analysis. So this talk was put together after looking at some bottles at a conference. So if you go to conferences, like in one of the main conferences, this actually was inspired by the Go to Copenhagen, Go to Aarhus conference in Denmark. One of the core features of the conference is at the end of the conference, day of the conference, you have to feed booze to the conference attendees. All right. So this is the conference dinner. It's in the Viking Hall in Aarhus. You should, if you ever get a chance to go to Copenhagen or Aarhus for the Go-To conference, it's an awesome conference. So this was the way that we were feeding booze to the attendees. You had to go and sit down. They brought drinks to you. But I think it was at QCon London where I saw this. So the conference is over. Everyone goes into a big room. All the attendees, you've got 1,000 people in a room. And what happened was waiters with about 20 bottles of Grolsch would just load up a tray and just go into the audience, and people would be grabbing bottles off the tray, and then they would, once the tray was empty, they'd go back and get another one. And I've never seen so much beer delivered to so many people in so little time. It was the most efficient way I've ever seen, because Grolsch is good enough for most people. If you wanted something special, you could go and stand in line and get a glass of wine or whatever. But it was amazing. Okay, so let's do some analysis on this. This is the number of minutes from the start. So they spent like a minute or so getting 10 drinks open on the first tray and getting out there. So the first time to the very first person to get a beer was 1.9 minutes. They got a mean, within 3 minutes on average, everyone had a drink. And then somebody was like queuing for like a glass of wine and didn't want it. So it took like 60 minutes before one person got a drink, whatever. Right? That's sort of the idea here, statistically, and there's some graph data, whatever. So then there's this plot. This is called a Cockcroft headroom plot because I invented it. And you can get the code in R is on my GitHub. So it's a response time versus throughput scatter plot. And you kind of intuitively know that as you increase throughput on something, it runs okay for a while, and then it starts to slow down a bit as you hit bottlenecks and contention, right? That's sort of the way you expect. So this is the normal behavior you'd expect to see. So you see on this, there's a line showing that as you increase throughput, the response time gradually starts to increase. And you're sort of hitting a bottleneck somewhere around the 10,000 point in whatever the graph this was, right? Okay. All right, so then they had another conference, and they decided that beer was boring, so they were going to do Mai Tais. And the problem with the Mai Tai is that only one person could figure out how to get those stupid little umbrellas open without breaking them. So they've got a little Mai Tai production group going, but it's got a single-threaded point of contention in it. And when you plot the throughput against response time, you get a linear thing, meaning the faster you try to go, the longer it takes. And so this is interesting. So now all I did was gather the throughput and response time data, and I plot it, and I can tell you this thing has lock contention in it, or it's out of threads, right? It's got lock contention. There's some single thread thing going on in there. So okay, that didn't work. Let's go back to the guy with the beer, but we're going to have an option now where you can have what I call a pineapple Dalek, which is an entire pineapple that's been hollowed out, filled with booze, and they don't normally arrange the umbrellas in Dalek mode, but after you've drunk one, you will arrange them to look like a Dalek. If you go to Hawaii, you can get these very easily, just about any bar. And so they said, we're going to have the option of beer or pineapple Daleks. And when you plot the throughput against response time, you get this very strange thing where it's either super high throughput or super slow throughput, but the response time isn't increasing. The graph is backwards. And what's actually happening is the people are out there serving trays of drinks, and then somebody asks for a pineapple, and that person then goes and starts carving a pineapple for the next 5-10 minutes. And eventually nobody is left serving drinks. They're all carving pineapples, all right? And so then you're in the low throughput, high response time part, the top left, and then eventually somebody finishes carving a pineapple, goes back to serving drinks, and then the system gradually returns to a high throughput. And you've actually built an oscillator. The system is not stable. It will oscillate back and forth. And this is what happens every time you have a system where you send it a mixture of fast and slow transactions. And you run out. And the slow transactions eventually occupy all the threads, and you can't get any of the fast ones through, right? Right, we've just got a few more minutes. So one more pattern. horizontally scaled, auto-scaled array of beers, right? You got to order your beers as a flight, right? Because you got to horizontally order, whatever. So here's an autoscaler. This is actually a graph from App Dynamics, where I persuaded them to build some of the plots, some of these kinds of plots into it. So this is the throughput over a day. It appears to be an actual Netflix data from an API of the Apple TV calls, where I didn't hide the number it was, but whatever. Probably from about 2014. And at the bottom, you've got the response time. And you look at them, well, they're sort of varying a bit, but you can't really see the pattern. But if you plot, and this is another App Dynamics plot, this is a scattered plot. And what you can actually see, so if you go back and say start at the lowest throughput, the bottom of the blue line, about 3 a.m., okay? The bottom lowest throughput is the furthest left point here. So what happens is more throughput comes in and the system gets slower and slower, and then it kicks up and installs some more machines. The autoscaler scales up and then it gets fast again. So what you're doing here is that the arrows pointing up are traffic appearing, and when it drops down is the autoscaler coming up. And then you get out to the highest throughput bit, and then the system goes idle and it starts removing instances. So the return path is after the peak coming back down. So if you give, the point really here is if you give me throughput and response time data for any system and I just graph it using my little thing, I can tell you it's well behaved, you've got lock contention, you're oscillating, you're going to have thread shortages, or you're autoscaling this thing. I can tell you that from the outside without knowing anything more about it by just looking at this behavior. And I thought that was cool, and I thought everyone should build it into their tools, but App Dynamics did a bit of it. Anyway, that was it. Thank you and cheers. And there are some slides on SlideShare. The Adrian Co. ones is my Netflix era ones, and then my Battery Ventures era ones are Adrian Cockcroft, and then most recently I've been putting slides on GitHub. Okay, well, thank you.